And yeah, without much further ado, I would like to hand over to Marta Garnelo. Marta is both a PhD candidate at Imperial College in London and a research scientist at Deepmind. She will tell us all about her awesome, exciting work there. And with this, let's give her a warm round of applause and enjoy.
Thanks, Simon. Hello, everyone. As Simon mentioned, my name is Marta. I am a research scientist at Deepmind, and I'm currently in my last year of my PhD at Imperial, meaning I should be writing up, which I am postponing as much as possible. And today I'm going to be talking about generative query networks and neural processes, which is work that we have done jointly with a lot of very cool people at Deepmind over the last year. Generative query networks, or GQN, appeared in Science this year, and neural processes we talked about at ICML. This presentation, as all my presentations, is very image and GIF loaded. It's meant to be a very high level and make people interested in what we're actually doing. If you want to have some hardcore math or discuss more specifics, I'm happy to chat to you about it later. And if you have any questions during the talk, then please raise your hand. My goal is to make you all understand this, so if I'm not doing it, I'm failing at it. So please, hands up and just ask a question, and I'll try to do my best at clarifying. There's many ways that we can motivate these two pieces of work that I'm going to talk about today. One very popular approach right now is meta-learning, or this concept of learning to learn, and those two definitely fall into that category. We can also think of them in terms of generative models. But the way that I'm going to talk to you today is a bit of a different one. And it actually is the way that we came up with these projects, which is rarely the story that is told in the papers. So we started off with GQN with a motivation for scene understanding. And this was a very specific application. And when we were done with our project, I was kind of motivated by the results. I kind of thought, can we not broaden this? And then that's where neural processes came out of. And this talk is going to illustrate how we went along with that. So I'll start with generative query networks, GQN. As I mentioned, the motivation for this was to carry out scene understanding. The lead authors, Ali Islami and Danilo Rezende, have been working on this particular problem for a while, and they were trying to figure out how to make algorithms that understand a scene once it's presented with some images from it. And now, you might think scene understanding is not that much of a problem or not complex enough. But let me give you an example. Assume you have this scene. And now you want to have an algorithm that learns how to understand what's going on in here, right? So current methods that you might have might involve, for example, as many of you know, just drawing bounding boxes around all of those, maybe even labels as to what objects they are. You hire some poor PhD student, have him do it for like millions and millions of frames, and then you train your algorithm, and eventually it's going to learn to somehow discretize your image and give you back some of the objects in it. If you say, maybe this is not enough granularity, you can even go beyond that and estimate pose, estimate gender, and so on. So there's lots of things that you can extract from this. And this is more or less, and I'm not going to say state of the art, but this is a very common approach to scene understanding. And while this is very useful, and it's being even applied nowadays in industry, you might think that there's more to scene understanding than this. First of all, the discretization of the objects in these images is somewhat arbitrary, even the resolution we do it at. Are we looking at a crowd? Are we looking at a person? Are we looking at an arm, a hand? Like, where do you even stop labeling something? And even if we knew how to do this, this would be such a vast amount of work if we wanted to do it for all of the objects in an image, for all the real images. So this does not seem like this is a viable approach. And this is where Ali and Danilo were thinking, how do we have algorithms that can actually carry this out with much fewer supervision, much less. So a few motivations of ideas that were going through our heads, and this does not mean that we solve it, but what you would want out of an algorithm is to give him this image, and it looks and it sees that those are humans, and it can also see that blonde human over there and understand that this person is a person himself. It's going to have a face. It's going to behave like the other ones it's looking at. Also, given this one image, if I ask you all to imagine what it would look like from the top of the stairs, most of you can probably come up with a scene like this or different variants thereof. But this is something that current algorithms were not able to do. And finally, if you want to go beyond that and you've classified the single objects, you can imagine what that scene looks from other places. Maybe your algorithm can go beyond that and actually understand at a semantic level what's going on. And it will tell you this is a very famous American late night show. and give you that amount of context. So these were kind of thoughts and motivations we had for this algorithm. We addressed some of them, not all. I'm going to go and talk about how we turned this into an algorithm. And the first thing we had to do to train an algorithm that is capable of carrying scene understanding is we go from the Late Late Show with James Corden to a somewhat simplified environment, which consists of, in our first instance, consists of a simulated room, as you can see. And this room is going to have a lot of different attributes. It's going to have different wall colors and textures and different floor colors. And it's going to have a number of objects in it. The number is variable, and the objects themselves are variable, their sizes, their colors. So there's going to be a lot of variation in our data set. And we're going to frame the entire task of scene understanding as, OK, if I have an algorithm and I show it what this scene looks like from 2 different points of viewpoints, if it can imagine what that scene looks like from a different point, then it must understand what's going on. It must learn about objects and occlusion and lighting and so on, right? So that's how we're going to phrase our scene understanding task. And then how do we translate this to an actual algorithm? So we're going to take our scene. We're going to have some observations, as you can see, as before, and the positions from which these observations were taken. We're going to concatenate those and just encode them into a representation. Because it's images, we're going to use convolutional neural networks, but it can be any type of encoder, really. And then what we want to do, this is all the information that each of these images gives us. We want to summarize that. And we found that one very effective way of summarizing these images without giving them any importance to the order is to just add them up. And this just worked, because the information that we have in this from the scene is cumulative, right? The more angles you see, the more you're going to complete your internal representation of the scene. And that's going to give us R, which is this one representation that captures this underlying scene, ideally. And what we're going to have here is some sort of decoder. You can have any type of generative model. We use draw, which is a big of a monster, but you can also use pixel CNN or anything really that you want. And we pass in our representation, so the knowledge about the room, some source of noise, so we can sample different ones. And then we just generate, we ask it from a particular new view, in this case V3, what do you think it would look like? And that's going to be the output of the network. So far, so good, yeah?
The V1i and V2i,
yeah.
Are both of those scenes like a video stream or something? Or are they just static images?
They're just static 2D images, yeah.
Is it always the same amount of images?
No, correct, very good question. Actually, you can train it to be, but we found that the more you vary, just like with the data set where we're trying to have a lot of varied shapes and whatnot, the more you vary the number of actual context points within like a sensible range, it helps. So we actually try to vary, and as you increase the number of observations, and we'll get to in a minute, you increase your certainty in your, yeah.
When you sum them up,
yep.
Do you normalize them afterwards?
Yes. Okay. You don't necessarily have to. We did experiments where we didn't have to, and the decoder learned to scale. But so that was, yeah, I mean, it kind of feels like it could work, and maybe not so much in terms of variance estimation, but it actually worked in terms of predicting the mean output. But yes, bottom line, we do normalize, although we somehow got away without it at some point.
In addition to that,
yeah.
Did you train the network before on like primitive shapes? Like
no. Yeah, no. This is all from scratch. Very good question. Yeah. So basically, we took the entire thing, trained it from scratch to like reconstruct this. We obviously have the ground truth. This is actually the predicted view, by the way. This is not an example. This is what the model predicts. And then we propagate the error and train the entire thing end to end. And it's just to point out again, this image itself has been generated pixel by pixel. We're not using a render. This is generated by a neural network. And then and we did this. And okay. What is important here is that we're not just training on a single room. And this is a bit what makes the difference between more traditional methods and this meta-learning training regime. What we have here is at every iteration, training step, we're going to sample a new, different, unseen room. So the model cannot just overfit to like a single room and single set of colors and objects. It has to learn to use whatever context it gets, because it has no other way of actually then predicting what the other view is going to look like. It has to learn to make use of this context. Up until then, have some prior over what patterns are, but nothing more than that. And then once it's seen some context, actually make predictions about the new viewpoint. So, and this is going to be important also later on for the neural network. Yep.
Yeah. So that means you're not only training the images, but also having like a label of the position or something, right?
Mm-hmm.
Perspective, vector or something, so that
yes.
when you ask it later for the predicted view, you have basically as a question something like, the vector with the direction where it should.
Yeah, so that's this V over here, exactly. So we concatenate with the V's, and here we ask for a new. And you can, the good thing is once you have an R, and we'll see that later as well, this you can do in parallel. So you can query as many as you want.
Okay, yeah, thanks.
Does that make sense?
Somehow my V association was with volumes. No, I don't know.
Not volume, view. But yeah.
So these must not be learned, so they are given.
They are given, correct. Yes, it is. There has been follow-up work in trying to remove this V aspect, which is a bit of counterintuitive because it seems important to learn about the space and relative distances, which is a GQN SLAM. I think it's been accepted for some workshop at NIPS. So it's learning, it's called SLAM, but it's using GQN to actually do localized mapping in some like Minecraft environment. So if there's any interest. Sweet. So what I'm going to show you next is what happens is, as you say, we take this V and we query different ones. Once it's been trained, we show it some images of the room, and we're going to query different positions, and we're going to query them very close to each other, so it looks like we're walking around in a room for like aesthetic purposes, but really it's just us querying different positions. And what you can see here is all what we fed to the model. This is the only image we've provided, and you can see from what it's rendering as we move around that it has learned a few things. First of all, it's learned about objects. It's learned about important things like occlusion and lighting. It's learned how like the 3D relations work, and it's able to capture, I mean, obviously we're giving it very informative views. For example, once you get this, it's going to be sampling a bit of noise, but here it's gotten a few of them, which goes back to the question over there. It can deal with a varying number of observations, and it's able to render this from a neural network. So it's exciting because it's learned to do something really, really cool. So we thought, okay, let's go beyond this. And the next GIF is going to be a bit more elaborate, so I'm going to explain. What we're going to work here with, we're going to go beyond the little room where the main focus was on objects and relations. And now we want to see, can this thing move around and understand more complex rooms and more complex spaces? And we're going to create these randomly generated little mini mazes that have different wall colors, also fairly random, different floors, and different like holes or shapes wherever. They're usually of this square size, but then minus the holes. And what we're going to do is we're going to pretend to have an agent, basically the one that is collecting the views, but this is not an RL agent, it's just for visualization purposes. And what we're going to do is it's going to move around and get some views. So you can see these four gray ones over here are going to be those four at the top. That's the context. That's what we know so far about this maze. And then we're going to move around and query at different positions and ask it, okay, what does it look like? And this is what it's going to its predictions about what it's going to look like. And then this is the actual ground truth as we know it. So we can see here that with those four, which again, granted, are fairly informative, and we'll get to less informative later, it already does a very good job at almost pixel perfect reconstruction of what the scene looks like as it moves around. And then the question we can then ask is, what happens if you have less information? And in order to understand it, it's more useful to think about top-down view. What we're doing here is we're asking it to predict what it thinks the maze looks like from above. Okay, so rather than just from the front, what do you think it looks from above? And what we're going to do is we're going to start with very few observations and then move around and collect more and more, and at every time step ask it, what do you think it looks like? And because we had that source of noise, I don't know if you remember the Z, we're going to have different predictions at every step. And you can see that as it collects more and more observations, the uncertainty is going to be smaller, so it's going to sample something that is much closer to the ground truth, whereas at the beginning it was just sampling all over the place.
Is there any way to get the uncertainty out of the model?
Yeah, you see, good, very good. Yeah, we'll get there. That's what neural processes is all about. But yes, and there's also, we have some measurements in a minute. Haha, perfect. So, uncertainty. Yes. So this to us was a really exciting property actually, because this is not something that all models learn to model their uncertainty given the data set, of course, so it's seen how these mazes vary, and then given the context it's observed so far. And we measure the uncertainty by measuring the information gain between having an observation and not having it, given the current context points. And what we're plotting here is, okay, we start off with no observations. This is how much we think the information gain will be, or how high our uncertainty is at certain positions. And it makes sense that along the walls it expects not much, because it knows that it usually ends about there, and in the center it's higher. And then as we increase the number of observations, you can see that the uncertainty is going to be reduced in places that make sense. And this is actually really cool, and this is what then was my main motivation to actually go on with neural processes, the fact that it learns this uncertainty. Yeah? Hi.
So
pick the observations itself according to informativeness?
This is us just walking around and saying this. We're not trying to do any optimization here. It's just.
The first one on the left side looks a bit strange. It's not
No, it's just random walks of like, I think we were trying to visualize, make sure that you see that it gets reduced rather than, and we come back to this actually later. So calculating the uncertainty in this particular, because GQN was not made for this uncertainty estimation, calculating the uncertainty is very expensive because you have to, for every pixel, calculate the information gain, assuming you get the image from all possible like viewpoints, average over those, and then go for every pixel in the thing. So it's unbelievably expensive. Later for neural processes, we actually do care about the uncertainty, and we'll see that we do use that for things like Bayesian optimization. For now, this is just, here's your uncertainty given that I've given you some random points to work with.
The uncertainty kind of means that you have like now a heat map where the optimum spots are, like the red ones are the optimum spots that you need to measure in order to get like, in order that you need like less training data to come up with the same kind of rendering afterwards, right?
Yeah.
So that means it's, on one hand, it could be used as like an absurd amount of compression algorithm for everything 3D. But on second, you could basically then, my question is more like, when you pick only like the optimum spots for that labyrinth or so, and then train it only on those in a reduced data set, how does the error rate compare to the initial model or the initial training that you had? Is like the uncertainty map dependent on the training data, or is it independent and can show you what you actually need in the data set to come up with the same kind of training effect afterwards?
Yeah, so the uncertainty is going to 100% reflect the data. So these models learn to, and this will be much clearer with neural processes as well. If it's always 100% in all of the maps seen that this corner goes like this, it would have no uncertainty that that corner goes like this. There's no way it would be a super certain. The reason it's obviously very uncertain here is because it's seen that it's very likely there's going to be some hole or some shape. So it's reflecting just the data. So probably if you then use that to train, you would bias it in that way, but which, yeah, can be desirable. Sweet. And there are other, okay, so coming back to this, uncertainty, pretty cool. But there were other cool properties about GQN as well. One of them, for example, is if we look at the representation itself, which we had not really optimized for. All we wanted is something that captured our scene, right? We had not really tried to like put any constraints on it. And what we're doing here is we're clustering, it's a t-SNE plot of the representations of different images. So each of these images, when encoded into one of these little R's, gives us one of these dots. And the dots indicate, the color of the dot indicates what room this comes from. So different colors of different rooms. And if we look at the representations we obtain with a trained GQN when passing these images through, we can see that they cluster very nicely by room. Whereas in a traditional VAE, where you don't want to have this, you don't have the spatial task basically, the representations are all mingled together. And generally, if you look at it, they cluster more by pixel similarity, which usually depends on what angle you're looking at, what corner of the room you are, because the wall and the floor give a lot of pixel loss, right? So that's what they're going to be clustered by pixels, whereas here we have a much more semantic clustering, like a similarity at a higher level. And this is especially impressive if you look at those two rooms over here, which have the exact same objects and the exact same colors, but just different orders within the room, and it still learns to tell them apart. And I don't know if I'd have to sit down probably and think about it, but yeah, no, I guess it's not that hard. I take it back. I think a human can do it, but it's definitely not trivial from a pixel loss point of view.
Well, it will tell you like the similarity between different scenes that it learned, right?
Yeah.
Because you can identify the similarity as well.
Yeah.
Not only the uncertainty, but also the
Exactly. So this is a different, yeah, hi.
Does this also encode for the real distance in the room?
For the what?
For the real distance in the room, if I show different observation that the distance is, the similarity in this representation is also is similar to the real distance in also?
I see what you mean. We've not measured that far, so we've not checked exactly what the representation would be if we moved an object or not. Part of the reason is also that these representations, while they show some compositionality, and I'll get to that in a moment, they're not completely disentangled the way you would have a beta VAE or something like that. So it's not clear what value would correspond exactly to the distance. But yeah, so they're still a bit of a mess, like with all deep networks. Sweet. Here we go. Another cool characteristic of GQN that we also somewhat got for free is the fact that by training with such a varied data set, we also got a very nice generalization ability. So what we did is we trained GQN on loads of different spheres of all colors except for reddish-looking colors. And also the same model we trained on a lot of red objects that were all object shapes except for spheres. So it's never seen a red sphere. And then at test time, we show it this. And we ask it, like, can we reconstruct it? And it's able to reconstruct it. So this shows that it has learned some sort of compositional representation that helps it generalize to unseen examples, which we also think is pretty cool because it's not something that's very common in deep learning at this high level, basically. So those were the properties. I'm not going to go too much into all of the experiments of the paper. There's a cool other applications. We did Shepherd's-Metzler, where rather than having a room, we're rotating an object. And one of the things that I was doing as an intern was basically to train GQN on a data set of a robotic arm. And then we showed that the representations obtained with this were actually quite useful for RL, so much so that we can then train an RL agent, reinforcement learning, where at every step we changed the camera view and it was still able to carry out a reaching task. And those videos made everyone so sick. So it was actually more impressive when watching the videos. But it was quite exciting, actually. And obviously A3C could not learn that. Cool. So to summarize it, when I finished when we finished working on GQN, for me, those were the three main characteristics that I felt this is why this algorithm is cool. Besides all the cool GIFs and whatnot, I thought, first of all, the fact that it's so flexible. We're not just learning a single room. We're actually learning to, at test time, take into consideration a context and then use that to actually make our predictions. The fact that it can estimate uncertainty, and also the fact that it's able to generalize to unseen combinations. Those three, for me, were really cool. And then I thought, OK, this is a very particular set of tasks, which is scene understanding. Can we go beyond this? And this is where we thought of generalizing GQN to not just scene understanding, but it started as a regression. For me, I don't know if any one of you does Bayesian on parametrics, but I was close to the GP literature, and I thought, like, this reminds me a bit of a GP. And what we're going to do here is we're going to take the whole concept and go away from just scene understanding, where our data set is going to be distributions over entire rooms. So every iteration, we're going to just pick a different new room and show some observations there and make predictions, and then a different one. And we're going to just simplify it all and say we care about regression. So we're going to have our data set is going to be a whole distribution over functions rather than just a single function. And this is actually also quite an important point, because this is what makes the difference between few-shot learning or meta-learning approaches that are being very popular right now and the more traditional approaches. Traditionally in machine learning, you're just trying to approach a single function. This is, for example, in reinforcement learning, where you have a single value function. You just observe loads and loads of points on this function as you go with experience, and you hope that at test time, it generalizes your parameters learned from that one function, generalize well enough to unseen observations. In meta-learning, what we're going to do, or in few-shot learning, is at every iteration, we're going to pick a new function from our data set, whatever that data set might be, and then get some context points of that, predict on that particular function, and then put it away in the next iteration, pick a new function. And what this is going to give us is that we're going to be flexible over this whole distribution of functions rather than this one overfitted function. And this is how we came about with neural processes. So smooth move into neural processes. I'm going to give a quick overview over how neural processes work and how they're trained, which is very similar to GQN, because it's a very similar model. Let me know if you have questions. So basically, with conditional neural processes, what we're going to do is, let's assume we have an underlying ground truth function, okay? And it's unknown to us. And the only thing we're going to be given on that function is a few points. Those are those red points. And we have the x and y coordinates for those points. And what we want to do is we want to estimate the value of a certain target position, x, the value of y there. So we want to estimate this point over here. So that's what we have. And what we're going to do, very much like in GQN, we're going to take those pairs, we're going to encode them using the same shared encoder into individual representations. And then these representations are going to capture all of the information provided by each of these points. And then we're just going to aggregate them into a single representation. And again, taking the mean as enough, because in this case, the information content is cumulative. Finally, we're going to use this representation together with our new target position, and we're going to pass it into a decoder. Now, what this decoder is going to produce is it's going to give us both a mean and a variance estimate at that position. So it's going to parameterize a Gaussian. Where am I saying it now? And crucially, once we have calculated this R, we can use that R in parallel and just query at as many positions as we want, as you can see there, and just go with that in parallel. So this also makes it very fast. It's just a single forward pass. So how do we train this? What we're going to do during training is we're going to get a function, for example, from a GP or images or whatever. We'll get there in a minute. We're going to get a subset of the points as our context points. Those are, for example, the green ones. And we're going to get some target points. And we're going to get the context points, encode them into one single representation, the information that we know from the context. And then we're going to pass them through a decoder. Together with a target point, we're going to pass them to a decoder and then predict the mean and the variance at those red points. The mean and variance are going to parameterize the distribution, and then we can calculate the log likelihood of the actual target value under our predicted distribution. And then that's going to be our error that we can backpropagate and update our model. Does this make sense? Have I lost absolutely everyone?
My question is, are the measured points then also stored in the sense that they're used for contextual reference points, or how you call them? The y and axis that you measured initially, they were only encoded in the R, right?
Yeah.
And the R itself is basically the reference point for the decoder later.
Yeah.
So that when you additionally ask the decoder, hey, give me the new point and I'm now measuring, then it gives you I don't know, something with an error, and you backpropagate that. Is that also then measured, also used or encoded inside R or not? For the next question for the decoder.
You can do. No, the way you can do it's not. We could do it autoregressively, which we'll get to actually in a later part of the of the talk when we come to just neural processes. There's a latent variable version. But basically, no. At the moment, the way we just do it, we just sample context points, and then in parallel, we do a bunch of target points, and we update on that. And then we throw everything out, and then what we do in the next step is, okay, we're done with that function. We sample a completely different one, get some context points on that one, get some target points on that, use that to update the model, and then throw that one out, next function, and so on. So at every iteration, we're going to be swapping functions.
Yeah. I guess, yeah, but...
I guess, yeah, slowly.
Normally, that would be leading to an average description of all kind of functions, right? Because if you have the first function and the second function and the third function and so on, and only measure only 3 points or something, then you have the average of all 3 points, right? But the idea is that you overfit it for each function specifically, right? Or is it always the idea that you want to get the average understanding of each function?
So ideally what you'd like is that your data set has some sort of structure that you can learn from this. So the equivalent of this is in a Gaussian process, for example. The Gaussian process has a kernel, which describes, for example, how wiggly a line is. So if you trained on curves generated by that Gaussian process, you would like it to learn that wiggliness, for example, if that makes sense. Or if you train on images, you would hope that it learns the shape of a face, which we'll get to in a minute. You're completely right. If I give no context, you'd expect it to give you the mean because it has no context. But still, that mean should be informative, meaning it should have the right amount of wiggles or it should be a face or whatnot. So it learns to extract an implicit kernel, like the Bayesians drop dead when I say kernel.
The complexity of how to describe it.
Exactly. So you'd like it to learn that. So it's true that it's a mean, but it's still extracting something. Obviously, if you trained it on all the functions in the entire universe, then yes, it'd be like the mean and zero information. Exactly. So obviously, you want to build in some prior through your data set. So this is exactly the point. You're trying to do a very data-driven approach to learning some implicit kernel, if any of that makes sense. And while we're talking about GPs, ta-da, this is how it performs when trained on functions generated by a GP. So the way we generate our data set is we set some kernel parameters, and then we just sample functions at every iteration from our Gaussian process. And it behaves as we would expect. It's not as beautifully smooth as a GP is, unfortunately. But it does. So we have the black line is the ground truth. And we're increasing the number of observations, which are those black dots. And as we do so, the mean prediction, which is that dark blue line, becomes more and more accurate. And more importantly, and this is where we go back to the variance, the output variance is actually reduced as we get more context points, and it gets reduced in the right places. And the reason it does this is because the model learns that if it has an observation nearby, it can afford to reduce the variance and get a higher reward signal, so to speak. Whereas if it's far away from any observations, it can still get some signal if it makes a very high variance, right? So that's kind of how you can think about it. Sweet. So to make it a bit more interesting, because obviously, why would we learn a GP kernel if we already have a GP kernel? Then it's much easier to just use a GP. We looked at this example, which in my head was really intuitive until I went to ICML and no one understood it. So I'm going to bear with me while I explain this. So we were regressing images, which doesn't mean generating images. So you take an image, Okay, and imagine the image is going to be your 2D surface, and that's going to be the position of the pixel is going to be your x. Like if we have a function, the position is the x, and the color is going to be the y. Okay, so you get some sort of like funky looking function of like pixel position and color, right? So what you're doing here is you're actually given some pixels positions and what color the pixel is at that position, and I ask you, okay, given that this pixel is like yellowy and this one's brown and this one's pink, what's the color of this pixel at this other position, right? And I can ask this for all of the pixels in the image, and it gives me one beautiful image. Keep in mind that this is not the same as a generative model of an image. That's a whole different story, and obviously they're going to perform very well. This is a regression problem in the hidden shape of an image production. So what we can see here is what happens as we increase the number of context points. So this shows us the black is there is no context points, and this is the only observation we're seeing. And like we said, it's going to show us the mean of what a face looks like. And the variance, interestingly, is going to be placed also in an intelligent way. So it's going to, obviously the background is usually what varies the most, and then a bit the edges on the head and whatnot. And then as we increase the number of context points, it goes from being a beautiful woman over to the man it actually is. But that shows you the bias in the celeb A data set. And it's eventually it does an okay job at like reconstructing this function. And also the variance is reduced significantly where you would expect it. And this is quite cool because, and it's shown here, we compare a model to k-nearest neighbors and GPs. Now this makes us look really good and GPs look bad, which doesn't mean that GPs are worse. They're absolutely not. This is a bit of a trade-off. So if ever you have a problem that you can describe with a kernel and isn't very, very high dimensional, then for sure go with a GP. They are mathematically sound. You're going to have guarantees. It's beautiful. However, you might be in a case like this one where how do you describe the kernel of a face, right? That's a bit harder. And if on top of that you have a lot of data, which you will need, then it might make sense to train something like a neural process because you're hoping that it learns this implicit kernel over faces, for example, from the data, right? So it's a bit situation specific, but we can perform well. And then it makes sense, obviously, that at the beginning, with very little information, we're already doing pretty well compared to a GP. And obviously a GP, once you have the whole information, it's going to do much better because they go exactly through the mean and they take the considerations into account, the context. Finally, we wanted to go beyond regression. It feels like this is a training regime that is general enough to be applied to many things. So we took neural processes and applied them to few-shot classification as well. In this case, you can imagine the x value are going to be, each x is going to be an entire image. For example, an omniglot image. Yeah, sorry.
Just a small question.
Yeah, go for it.
How will the variance, like the uncertainty, perform if you have an example not from the same basically domain, so other?
Completely different. It's still going to show the variance it's trained on. So this model, this model is very good at extracting the kernel and the variance, which is the same, the variance from your training data set. So you're hoping that the way I think about it is in Bayesian nonparametrics, when you are creating a model, you impose your prior knowledge by choosing a certain kernel and say, this is how I am going to influence what my kernel is, like what my model is going to be able to model. Here, the way you're influencing what your model models is through the data set. So if you mess it up and use a data set that is very different from what you actually want to test, it's not going to work because it's a poor choice. Just like if you choose a kernel that is not fitted for your actual ground truth, it's going to predict the variance that makes no sense, right? So it would do badly, and it's a neural network on top of everything. So probably do badly in a very weird way in the idea, yeah, unfortunately. Hi.
You predict mean and variance, so can your method also predict a multimodal uncertainty, such as diverse faces that would be plausible?
You guys are leading me through my talk. Yes, we'll come to in the next slide. Let me finish with classification and we go there. Yes, this is the short answer. Yes-ish. We hack it our way. Okay, so just classification real quick. We take, in our case, the x is going to be a whole image, is the omniglot image, and then the y is just going to be the label, right? And what we're going to do, exactly the same as before, we're going to encode the images and their corresponding classes. We're going to aggregate, although only over classes, because if we smush them all together, we find that it doesn't ever learn. And then that's our representation. And then at test time, if we feed it some images, you can see that it does a pretty good job at matching them. And if you present it with an example it's never seen, like this one, which is none of the classes shown, It's going to have some uncertainty over which one it is, and usually also kind of match it to those that maybe are somewhat more similar looking. And we do okay. I mean, matching networks are pretty good okay, but, as well, but we didn't want to super parameter tune, so it's up there. And crucially, our runtime, because we have this bottleneck where we aggregate over everything, is going to be n plus m, where n is the number of context points and m the number of targets, whereas algorithms like matching network do all-to-all comparisons, so they're going to be n times m. Sweet. So to answer your question from earlier, right now, what I've been showing you, it's called conditional neural processes, and it's what came before. We call it conditional because we cannot really consider it a stochastic process the way we wanted it, because it's completely deterministic. And it only has the sampling at the end. Our follow-up work is neural processes, and this without the conditional, which was very confusing because shorter names apparently come first. This is what motivates that follow-up work, which is exactly what you were asking. So far, if given a certain ground truth image, I give you some context, right? What I've been showing you so far is the mean prediction, right? The average, like that blue line and the GP of what was happening. Because here, given a certain target, we're predicting the variances independent of each other. So we predict it for every single data point. These variances are going to be independent. So if we thought, let's generate different faces by sampling the only distribution that we have, which is this output distribution, we're going to be sampling independent values for each of the pixels, right? Does this make it, because it's a variance, not a covariance, yeah?
Does it mean the variance is used for multiplying on top of the color space? Did you mention before, because we have like a 3D representation of the color space plus the pixels? Is the variance then just multiplied on top of that?
The way you do, you mean for sampling?
Yeah.
This just parameterizes a mean and a Gaussian. So we have this mean, and then each pixel has basically a Gaussian distribution. But all of these are separate from each other. In GPs, usually you have a covariance, so you can sample entire trajectories. Whereas here, each pixel is on its own. So if we sample, we get this mess over here. You can still see that it's a mean somewhere there, but every pixel is going to be in a different image, right? And now there's a couple of ways we can give this some global consistency. So we can, one of the ways would be to do autoregressively, which we also talked about. So what you could do is you can say, okay, I sample this pixel, feed it back in as my context, sample the second pixel, feed it in as my context, and so on, and you do the entire image, right? In that case, they would be correlated because they've been conditioned on each other. The problem of doing this is that these methods tend to be very slow. That's like what pixel CNN does, for example. Another option could be to model the entire covariance here. So rather than just the variance, it would be the entire covariance. And here again, it's not clear because it starts getting very similar to a GP, and then we have again the runtime issues of like comparing all to all and whatnot. So we came up with a different solution, which was to introduce a latent variable. So if we look at this bit over here, what we're going to do is rather than having our R over here, which is what we had earlier, and just feed that in as our deterministic representation, we're going to say, okay, R actually encodes some latent variable, so some Gaussian and latent space. We have the mean and the variance. We can sample our latent variable and then condition all of the pixels on this one Z. And then every time we sample Z, we're going to get a different face. But this one Z is going to be the same for all pixels, so it gives us global consistency while still having the chance of actually sample faces, if this answers your question.
So the context pixels are constant in this?
Yes. Yeah. And then obviously the more context you have, the more similar those would look, but at the moment it could really be anything from that.
Yeah. But I didn't quite understand the transition from the mu's and sigmas to the z.
From here? So what we're going to do here is A used to give us just a vector that was a representation, right? So what we can say is, okay, this vector actually is going to encode a mean and a variance. And we're going to say, okay, this distribution we sample, our model is going to sample whatever representation. It can choose whatever, however, it's going to be a Gaussian with a mean and a variance. We sample this, and then this is fed to the model as like, it's like a normal latent variable model, like you would do in a VAE, for example. You know, a VAE also encodes a mean and a variance in latent space. So exactly the same, only here. Somewhere there, questions? We good?
How do you get the sigma set for training?
So what we are going to do is, what I found easier, but it's also worked without really, is we fix this one, so this one's fixed, and then that one it just learns. A bit like it learned the other one before.
How is it learned the other one before? How do you learn the variance?
So in the previous one, because we're telling it that the output is going to be a mean and a variance, right? In order to calculate the loss, you're going to take the likelihood of that distribution, of the real value under that distribution you defined, right? So the model learns that if it has a context point nearby, chances are that it's going to be a similar one, so it can afford to put the variance down to get a higher reward signal. Whereas if it has no context points nearby, it's better to put a big variance and then get somewhat still of a reward. That's kind of the intuition behind it. We have no quantitative analysis of it, but this is otherwise either that or black magic. So I'm hoping, that should be it. And
so actually, it's like, so you could also implement something like the supersized neural network, like the ones that basically learned how images are supersized and encoded or shrink down. Something like that could be implemented that super easily, actually, because the sigma actually has the same effect, right?
yeah.
Because if you have, like, I don't know, 16 by 16 image of the same person, you can also, like, supersize it, but you would of course need more context points for that matter, but it would basically come up with a face that would actually look like the person.
Yeah, and this is what we did also in the paper, if you're interested, actually. That's a good point. One of the good points about neural processes is their flexibility. Because we're assuming that it's a regression task, we can sample at pixel level, so whenever the intervals of a pixel is, but even at sub-pixel level. So we do this in the paper, and we do exactly that. We go from from a CELIP A 32 by 32 to like 100 and something, and it looks smooth. Obviously, it's not going to get freckles and details because that information isn't there, but it smoothes out and makes like a nice face. So definitely we can go beyond just pixel level. Yeah.
Except if you train it specifically for those kind of features. Because if you have, like, I don't know, as a context point, like all the lips, for example, and only choose them in that specific area, then it will learn that, of course, and then if you resize it to a bigger output image, then it will, of course, come up with the details then. Because the context points are more detailed there. Right?
They are, yeah, to a certain degree, obviously.
We're assuming only that context points are totally random,
yes,
and not in specific areas, like not specifically to the nose or
the
eyes or the ears, for example.
But yeah, and obviously to a certain, to the resolution there we have. So we use this model now where we can so what this model gives us, bottom line of this, is basically before, if we had a certain set of context points, we could not sample different possible scenarios. We could do our mean, and that's all we could do. Now we can actually do entire coherent samples that we can generate one after the other and get different possibilities. Here's some math for those of you who like it, the mandatory equation slide. This all I want to say about this, so that I think the way we implemented this is one of the things that if you're Bayesian, you might think it's interesting. Basically, when we're calculating the elbow, it looks really intimidating. Forget about all of it. It doesn't really matter. All we're saying is in the KL term, which is a term that is comparing the prior and your posterior and trying to not make them look too different, we implement the prior and the posterior both as the same network, where one has more information. So the prior is going to be the network that encodes what it's seen just with the context, and the posterior has seen both the context and the target. So basically the posterior is just a more informed version of the prior, which is a Bayesian way of thinking about this. All this is saying purple is prior, blue is prior, pink is posterior, and they're implemented in a similar way. Sweet. So what do we gain from actually doing this latent variable model? This is what I was showing you earlier, where all we could do was plot the mean and the variance, and that's it. Now we can actually draw different samples. So given some context points, we can go and sample entire trajectories. Because we're estimating the variance in latent space, it's not perfect. It's not as good as the CNP is going to be, or let alone a GP, but it's at least learning the right thing. Yep.
You're just showing the mean on the, like the
Yes,
output?
yes. Correct. But we're sampling in latent space. Yes. Why might this be useful? There's a number of applications, and we've done this on images and everything again, but you don't need to see the other MNIST faces again, the MNIST numbers or CELIB A faces again. It's things like, for example, Bayesian optimization, where you can use Thompson sampling to find a global minimum. The way this works is you're going to have some estimate over what the function looks like, which originally is going to be pretty bad because you have only one observation. And you're going to take whatever the lowest of that is, get the actual value for that, and then update your estimate over what that function looks like. Say, okay, which one is the minimum now? It's here, and so on. Am I doing it right? Yeah, until eventually you actually find the lowest point. And this requires you to sample a trajectory at every time that agrees with the observations you've seen so far. And you want it to be sampleable because you want to get different possibilities and not always get stuck at the same one. And we use this type of optimization problem and apply it to a contextual bandit problem, where an agent has to figure out how big the area of a circle is, the blue area, by just trying out pulling different arms, depending on where it's located. it looks a bit like the Chrome logo. It's not a very difficult task. Just it does Bayesian optimization, and we do fairly well. We compare against like MAML and so on, and it actually does really well. So we're excited that this works out of the box. Mind you, this also it requires you to pre-train it. Things like MAML, for example, doesn't need necessarily pre-training. They do these like gradient updates at test time, whereas we actually have to train on a whole distribution over functions, and then we can apply to it. So, yeah.
Yeah, so but you do not only have to sample a function from the current observations, but you also have to find the mean mode, so which can also get expensive in higher dimensions.
Yes, exactly. So at the moment, we've only done it for 1D regression. We're actually looking at optimization a bit more seriously now, and how to overcome this. It's actually still a somewhat open question because Bayesian optimizations, because GPs usually don't work in very high dimensional spaces to begin with, never had to really encounter the problem of how do I even evaluate my estimate in super high dimensional space. So that's another question we're thinking about, that we're kind of thinking about, but not quite there yet. Yeah. Cool. So just to wrap up and like maybe just summarize my thoughts on neural processes and on the whole thing, I guess. How do I see neural processes compared to the current regression algorithms? So when I think about regression algorithms, for me, there's two main players. We have, of course, neural networks. Neural networks are going to be initialized, or a set of weights are going to be initialized, the weights at random. They're going to produce a function. And then we're going to take loads and loads of data from that one particular function we're trying to approximate, and we'll update the weights in such a way that they approximate this function that we want to use. And then at test time or at inference time, what we hope is that those test points that we really care about are actually described well by this function approximation. Things that I think are really cool about neural networks is the fact that this function approximation is learned from data directly, which is really useful. The fact that it can actually model fairly complex functions because we have so many parameters to play around with that the complexity of the functions can be insane. And the fact that they're super fast to evaluate at test time. It's usually a forward pass and we're done. On the other hand, of course, there's Gaussian processes. Now, if we forget the search for a kernel, which is its own can of worms, there's not really any training phase per se. Instead, we're going to have this prior belief over what our function space looks like as specified by the kernel. And then at inference time, we're going to actually observe some observations. And those are going to narrow down our beliefs of what the underlying ground truth function actually looks like. But we're still going to learn this whole distribution over functions as opposed to a single rigid fixed function. What I think is really cool about GPs is the fact that they learn this distribution over functions. So this allows us to be flexible at test time. Depending where I put those context points, I can get loads of different functions, whereas here I can only get that single one. And also the fact that they have this measure of uncertainty, which I think is very valuable. With neural processes, we kind of try to combine the best of both worlds to a certain degree. Neural processes are going to model loads of different functions, but we're going to implement that as a neural network. So the weights are going to be initialized at random originally. And then we're going to use loads and loads of data, meaning these whole distributions over functions, to train our model. And this is going to lead us to some neural networks that have some belief over what the function space looks like. And then at test time, we actually get some observations, and that narrows down our belief over what the function space looks like, as seen here. And in a way, we still have some of these benefits that I was really happy about. We're learning this function approximation from data directly. We can model fairly complex functions because we're still using a neural network, and they're very fast to evaluate. We can parallelize, and it's only a forward pass at test time. On the other hand, we're still running a whole distribution over functions rather than that one single fixed function, and we have an estimate of the variance, albeit a variance as reflected by the data. So this is not just like some inherent variance. Yeah?
I'm just thinking.
Yeah, for sure.
But with the uncertainty that you actually also learned from the data set, would it be theoretically possible to reduce the network size based on an uncertainty factor, right? So that you figure out, hey, the uncertainty is pretty much okay, so I can reduce the outer layers or something. Like like I don't know, if you have, for example,
I guess so, yeah.
or so that tries to figure out like a timeline task or something.
Yeah.
Then you could probably use the uncertainties to say, hey, fuck it, I don't need those layers anyways, and they don't need to unfold over time anymore because I'm as precise as I want to be, like over 90% or something. Then you could also make trade-offs and therefore speed it even up by training it new data, right? Yeah,
I guess. Yeah, it's going to reflect something about your data. So basically, if what you say is if you realize that certain aspect of your data don't have as much variance or as high complexity as you thought, you can definitely prune it.
The uncertainty is also like, I don't know, stored somewhere in latent space, then you could also like let it learn more efficiently, like
Yeah.
in future, and expand more efficiently
Yeah.
over time.
Yeah. Although, yeah, slippery slope because it involves understanding your data properly, and this gets messy. Yeah. But yeah, quickly. Yeah. So with that having been said, plug. Yes, there is GitHub code for all of this, which took me a fair amount of work to get out the window. So basically, you can run the deterministic non-latent version on a Colab, which is this IPython notebook, Google version of an IPython notebook. And you can run it. It's all online. You can run it there, see how it trains. It's only for the 1D regression task where you're actually trying to do a regress a GP. We want to also get out the latent variable model and some extensions that are currently coming out of neural processes, but it does take a bit of a while to get stuff out. So anyway, you can go check it out and star it, which is what apparently people want. Yeah, and that having said that, I want to thank my great collaborators at Deepmind. They're all fantastic people. And if anyone has any questions, I'll take questions. Thanks. Go for it.
Can you elaborate more on this aggregation part of the network?
So, yeah.
What works and what doesn't work?
So the
aggregation.
Yeah. So the main problem is that what we tried the first time around worked straight away, and being lazy, no. So basically, we wanted something that was order invariant explicitly. So for example, if you know you're going to be modeling time series, you might want something that has more of a time series flavor, and then definitely LSTM, blah, blah. But no, we knew that we wanted order invariance. And the easiest way to implement the order invariance in a way that we know how to backpropagate and everything seemed to be either taking the mean or summing up. And we've only tried that. So far, we've tried that. There has been follow-up work on neural processes with a memory module in there, but that's fairly recent ICLR. But yeah, some in memory. That's probably one.
And this also applies for the phase generation network.
Yes,
So the
for
A-
everything, yeah.
The A block was just summation, more or less.
Yeah. Yeah.
Yeah, I find this surprising that such a simple method.
Exactly. No, we did too. No, it's. I think the reason behind it being that the information is always cumulative. So, for example, this didn't work so well in the case of classification, where originally I was aggregating over all examples of all classes, just smushing them together, and I lost too much information. It just wouldn't learn. So what we ended up doing is just aggregate. We know the labels of the context points, right? So we only aggregated over the context points that were of the same class, basically. So our vector, rather than being r by 1, it's r by k, but it's fine. So sometimes it can be destructive. I think because all of these tasks were it made sense that the information was additive, that you could just get away with that.
Did you also try the same because you mentioned that you were using a CNN for encoding data, right?
For some of them, for the classification.
Yeah, sure. Yeah. Did you also try out different other neural network architectures, like LSTM something, in order to classify different kinds of data, or did it only work specifically for CNNs, for example?
We haven't tried out anything. So we specifically stayed away from any recurrent type of network because we had this order invariance, so we were on this other. We've only really tried, so far most of these experiments have been fairly toyish. So MLPs, most of it is MLPs. This is literally the 3-layer MLPs on both sides for both the image regression and the GP regression. For the classification, we did, like I mentioned, need CNNs because we wanted, continents, because we wanted image data to be processed. We've not tried beyond that. I don't see why it wouldn't work. Usually this was just because it's very quick. They're actually very quick to train. The one in the Colab, you can train in in an hour and you have your solution. No.
Did you try to make this intermediate representation disentangled, just like the ratio of the encoders, like to make it explainable?
Yeah. We did not. Part of the reason also being that when we did GQN, there was a lot of analysis put into understanding whether it was disentangled or not, and it wasn't. And I think, I don't remember if we actually tried to make it more disentangled, but we didn't. We haven't really tried whether that works or not. It doesn't seem to be of importance, although obviously if you cared about actually understanding the structure, then it might be. I'm thinking if there's anything inherently, bad about it. could work. Yeah. Simon?
Have you tried scaling up GQN to more complex tasks? Like, for example, just running it in, say, a game environment where, just resolution and complexity would go up?
Yeah. So we've tried what am I saying? Minecraft, which is also what the SLAM paper has. But very quickly, even there, at some point it started being fairly blurry. I think the bottleneck with GQN was draw, because draw is a very big model with loads and loads of parameters, and it has these iterative cores that then have their own parameters. So it's a lot. So I think we would have had to scale it up a lot, and I think if we were scared of scaling it up, if we were kind of hesitant, then I don't know. It didn't seem very realistic. We're probably not at the point, or we're not 2 years ago at the point where we said it makes sense to scale this up massively. I don't think so. Oh, and also, data is fairly hard to get by. So yes, for video games you could imagine, but we got a lot of criticism saying, why don't you use real world? But you can imagine it's very hard to have a real world data set from the same scene, from different points of view with exact labeling of where you took the images. So it's fairly narrow in that sense, yeah, sorry.
Have you compared strategies to select new contact points based on the variance you obtained from sampling?
We have this in the first one where it's where we're not actually sampling but the output variance, and in the first paper of the CNP I should have added it. Basically we show experiments on MNIST on how if we randomly choose the context points, it gets better, the error goes up like this, and if we actually let it choose by wherever it thinks it has the higher uncertainty, it learns it much quicker and it just finds it. So it makes intuitive sense, right, that it knows where it would be most uncertain about, and it kind of works. But we've only tried it so far on these, we only showed it on this MNIST example, so yeah. Someone, yeah.
So what other models, other than draw, did you try, and what were the successful ones?
I'm not sure if they used pixel CNN or not. They might have. This was before my time, so I'm not sure. Really, anything that generates an image should work, just because of how it's built up. If you think about it, neural processes is kind of like a general version of GQN, and in that case, the decoder, rather than a beautiful image, is just one value usually. And in that case, because it's only one value, you get away with an MLP, right? So I think anything should really work. Any generative model of images, which at the time were either draw really the most powerful, or pixel RNN or pixel CNN. We went for draw because one of the people on the paper is also the draw guy, so he knew.
Does the sampling in the latent space actually change the uncertainty / variance estimate in the end, because you don't basically always propagate kind of a mean, but always choose a different one?
So the way I trained the latent one, and this has been updated in follow-up work at Deepmind, which I've not led. For me, I fixed the output variance. So I learned the mean, I learned the mean and variance in latent space, but I fixed the variance in output space. The reason being that usually when you have these hierarchical sources of variance, models just, one of them collapses, usually the one you don't want to collapse, or it learns something really weird. So in my case, for simplicity, I fixed the output variance, so it's not really learning it. So it's also not going to change, to answer your question, because it's fixed. It'd be interesting to see. Yeah, I haven't looked. I know that people have trained it with changing the variance, so I'd have to check up on them to see what happens there.
So the beginning was called neural rendering, right?
Yes.
So
is there
a way to invert it, like neural localization? Is it already built in?
I think localization would have to be if it was inferring the position, which it isn't, right? It's given the position.
So it's not in there. I didn't miss out on it.
No, you didn't. No, but this is where the other SLAM paper by this other guy, one of the collaborators, does do localization. So it does, do the inverse problem. Sweet. Anyone else? Good. I think there's donor pizza apparently.
Okay, thanks so much for the lively discussion afterwards, and thanks so much, Marta, for this exciting talk. Really great having you. All right, so I think in about 10 minutes or so we should have pizza. We ordered a bit late. But please bear with us. It would be great to have you. And you know, there's also some beverages outside. Looking forward to seeing you stick around. Thanks.
Thanks.
Marta?
Hey, yeah.
I was mostly asking because the idea that I had in my head, like, because you mentioned that you were using like the 2D pixel map, right? And
Yeah.
you had like color space as the encoding for measuring the quantity of reference points, so that you can